Welcome to Unit 4. Let's start talking about polynomial and rational functions. So what is the difference between a polynomial and a rational function? Well, polynomial, if you look here, basically everything here, this is the main part right here, non-negative integral powers. So all these powers are positive, which means you don't have any of this. Let me just make this smaller. You don't have any, like if I had 3x to the negative 2, well, don't forget that's the same as 3 over x squared. That would be a rational function, okay? Polynomial functions have no negative exponents, okay? So that's the main difference. So there are problems here of being undefined. In polynomials, you'll never have that problem because if you have a positive exponent, well, your denominator is always 1. Nothing will make that undefined. It's an important concept to consider. All right, well, you have odd and even degrees. And, well, let's just talk about odd first, one at a time. Okay. With odds, they always end in different places. It's either if it starts high, it ends low, or if it's the other way around, it could start low and do something like this and end high. Okay, the blue one here would be positives, and this right here, if you see, that's a negative. Okay, when it starts high and goes low. All right, now for even degrees, your x to the 2s, 4s, 6s, they'll always do the same thing. If it starts high, it'll end high, or if it starts low, it'll do something like this and end low. Okay? That's inherent with all even degree polynomials. And here the blue would be the positive, and the red would be the negative, with negative coefficients. Negative leading coefficients, I should say. Okay, now for complex numbers. Every number you think of is a complex number. You have imaginaries and reals, but every complex number, as you can see here, is comprised of both pieces. Okay? When I say complex number, you probably think something like, 2 plus 3i. Well, yeah, that's complex, but it has a real piece and it has an imaginary piece. So even if I gave you a real number like 7, well, 7 is a complex number because, yeah, it's real, but let's just consider its imaginary piece as 0i. Okay, 7 plus 0i, that's just 7. Or if I just had something like 4i, well, 4i has a real piece to it as well. The real piece is just 0. 0 plus 4i. And don't forget what that I equals. We'll be dealing with it now. So that is the square root of negative 1. So if we're doing some problems here and we get something like this, say negative 36 underneath, well, really what that is the square root of 36 times the square root of negative 1, and that would give you your 6i. Okay? All right, so what do all polynomial functions have in common? Well, they all have a bunch of terms. You have your highest degree term. We'll let n be your highest degree. And if that's my highest degree, we add these. I would then have whatever n is, that would be n minus 1. And then whatever n was, that would be n minus 2 plus ... Keep going on until you get to the x to the first term, and you get your constant. You can think of constants as having an x to the 0 with it, because that doesn't really change the value of it. Right? X to the 0 is just 1. All right, what else do all these terms have in common? Well, they all have coefficients. So what if I were to call the first coefficient, which is your leading coefficient. Leading, that's sloppy, but I think you can read it. Coefficient. Well, if that's a to the 0, this could then be known as a to the first, and a to the 2, and ... And whatever n was, this would then be my a to the n minus 1, and this would ultimately be my a to the nth coefficient. Okay? That's a general format for any polynomial function, depending on how many terms you have. And also keep in mind that whatever n is, n must be non-negative. N must be non-negative, because if it's negative, then you're going to have a rational function. Must be non-negative. Sorry about my ends there, but I'm sure you're used to it by now. Non-negative. Alright, now depending on how many terms you have, what if, say, you have like, well, something like this, x to the third minus x plus 1. What if you don't have an x squared term? Well, you really do. Your coefficient would just be 0. Okay, so everything has a coefficient. It would just be a 0x squared. Alright, here are a bunch of synonyms that I really would like you to know. These are all the same. Whether I'm asking for the zeros, the roots, the x-intercepts, or the solutions to a function, they're all the same thing. Where does it cross the x-axis? Well, I say that, but if they're imaginary, they don't cross the x-axis. And let's just start off with a nice easy one. Okay? If it crosses the x-axis and it factors nicely, well, that's all you have to do. You set this equal to 0. You might remember this from algebra. And you do this, and you do this, and what do we got there? We need a 6 and a negative 2. And if this thing times this thing equals 0, that means one of these have to be 0, because 0 times anything gives you 0. So you figure out what makes this factor equal 0, and what makes this factor equal 0, and you get negative 6 and 2. X equals negative 6 and 2. Do you know why? You ever think of why we set this equal to 0? Well, I mean, if you look at this graph, we're finding the x-axis. Well, these are the y values. Y is 5, 4, 3, 2, y is 0. So when y equals 0, all we're doing is figuring out what x values make that happen. Negative 6 makes it happen, and 2 makes it happen. Alright, so what if it's not that easy? What if it doesn't factor so nicely? What do? You might remember, hopefully you do, the quadratic formula. Let's do the quadratic formula. It is x equals negative b plus or minus square root b squared minus 4ac all over 2a. Ta-da! I sang it. Okay? So it's sloppy, but here we go. Negative b plus or minus the square root of b squared minus 4ac all over 2a. The whole thing is over 2a. Okay? And what's your a's, b's, and c's? This is your a, which is 1. This is your b, which is 4. And this is your c, which is negative 12. You could have used this anyway. If you plug in that a, b, and c, you'd still get these values. Okay, I don't want to bore you with a bunch of theorems, but we got to talk about a few of them. So here is the first one, the fundamental theorem of algebra. Alright, well, this is what we're talking about right now, polynomials in one variable. So long as we have something higher than x to the 0, we are guaranteed at least one complex 0. Now, it says real or complex, but remember, all real are complex. Complex numbers are broken into reals and imaginaries. Okay, so just a friendly reminder. Alright, the next theorem, really it's just an add-on to the one we just spoke about, and this is the one we're going to be the one that we're going to be interested more for our discussion. The corollary, which is just an add-on, because this one is true, this one happens to be true also. This one says what we're talking about, polynomials with a degree higher than x to the 0. They don't have to be distinct, but if it's a x to the 2, we're going to have 2 complex roots. And again, it says real or complex because people forget complex are real numbers and real numbers are complex numbers. But you know, it doesn't have to be distinct because, say for example, you have you factor something, you get x minus 2, and you get it has 2 roots. It has x equals 2 and an x equals 2. This is just called a double root, but it does have 2 roots. Okay. And if it's an x to the 6th, well, we are guaranteed to have 6 complex roots. All right, what else we got here? So anyway, like I said, this is going to be a useful one. We're going to be looking at the highest degree so we can determine how many complex roots we have. The linear, and I'm leaving these up here. If you need to pause this and jot it down, be my guest. Okay, so the linear factorization theorem. Sounds so formal. Again, this is what we're talking about. Polynomials, something greater than x to the 0, can be factored as such. You may have a coefficient that you could take out, but you can break something down into all of its factors. Because if it's x to the sixth, we have 6 complex roots, means I can write 6 factors here. They might not be distinct, they might be a couple of them the same, but I can write them as the factors. Pretty cool. Alright, well, let's do an example. Let's start with a third-degree polynomial. Now, based on what we just read, a third-degree polynomial is guaranteed to have 3 complex roots. They may all be real, they may all be imaginary, it could be a combination of the two. Let's find out. So let's do this problem right here. Okay, we have x to the third plus 4x squared minus 2x. Now, no matter what you're doing, you should always, if you see a common factor, take out a common factor first. I notice they all have an x in common, so let's do that. And we have 4x minus 2. Okay. Well, if the trinomial there factors nicely, great. Let's see what happens. X, things that multiply to be negative 2. Well, there's not much that's going to multiply and be negative 2 and add up to be 4. So guess what? Doesn't factor nicely. What do? We're going to use the quadratic formula. Now this factor right here, that one is we can take that one out and set that equal to 0. But when we set the other one equal to 0, it doesn't factor nicely. So we have to use a quadratic formula there. Okay, we do have a root right there, x equals 0. To find the 2 over here, we're going to do x equals negative b, which is negative 4, plus or minus the square root of b squared, minus 4 times a times c, all over 2a, 2 times 1. That will give us negative 4 plus or minus the square root. So this right here is negative 8. Negative 8 is plus 8. 16 plus 8 is the square root of 24. And that's all over 2. And you can do some simplifying here. If you don't remember, let's see, the square root of 24. I can get the square root of 4 and the square root of 6, and that would be 2 radical 6, and that would be simplified. So we could rewrite it like this. X is negative 4 plus or minus the square root of 2 radical 6 all over 2. If we wanted to do more simplifying, we could take a 2 out of everything and we'd be left with this. X equals negative 2 plus or minus radical 6 all over 1. Well, those are our 2 other real factors. We have negative 2 plus radical 6, which would give us a decimal, and x equals negative 2 minus radical 6, which would give us another decimal. And that would be 1 root, 2 root, and over here, 3 root. Okay, those are our roots. All the work here we just did, nothing changes. If we did have imaginary roots, the only difference is that would have come up right here. We would have had a negative under the radical, and then we would have had a couple imaginary roots. Alright, so sometimes we'll have to be working backwards. Rather than having the function and trying to figure out the roots, we'll be given the roots and try to figure out the function. And that's what we've got to do here. So we're going to write the polynomial of least degree. It says least degree because it could be a degree or 2 higher. It could be higher degrees, but the minimum degree it's going to be. And we can figure that out. Well, let's see what we got here. What does this tell us right here? 2 plus 0y is 2, and 2 minus 0y is 2. This is just the real number 2. I'm just reminding you that real numbers are complex numbers. You can write them as complex numbers. Well, this one over here, this actually does give us 2 different x values because x plus 3i is 3i, and 0 plus 3i is 3i, and x equals, 0 minus 3i would be a negative 3i. So right there I have 2 different imaginary values. Alright, well, from these 3 roots, that's going to give us a third-degree polynomial. Let's work backwards. If the root is x equals 2, that came from the factor x minus 2. If the root is x equals 3i, then that came from the factor x minus 3i. And same for here, that would be x plus 3i. Alright, well, those are our 3 factors. Now let's continue again. My suggestion, multiply the I terms first, because when you do this FOIL right here, you're going to get an I squared. Who remembers what I squared equals? Well, we talked earlier that I equals a square root of -1. So if I were to square both sides, what would that give us? I squared would equal -1. Okay, so you're always going to substitute in an I squared with -1. All right, let's do the math. We can say in that color. So I'm going to have x minus 2, and let's do the FOILing here. So x times x is x squared. That is a plus 3xi. You can write that however you want. Multiplication is commutative. And then this over here is going to be a negative 3xi. And then over here, negative 9i squared. Okay? Don't forget, I squared is the same as -1. So we have x minus 2 times x squared. These two cancel each other out. And if that's a -1, -1 times -9 is a positive 9. Now let's FOIL this. Let's change the color to red. So we got x times x squared, x to the third. That is a plus 9x. That is a negative 2x squared. And that is a negative 18. Usually write it in descending order based on the exponents, so let's do that. X to the third minus 2x squared plus 9x minus 18, and that is your f of x. May your note-taking on that video have gone smoothly. May everything was clear. Anything that wasn't clear, put a little asterisk next to your notes and ask me tomorrow when we get into class. We're going to work on day 1, polynomial functions. We are going to do page 181 and 183 tomorrow in class. See you then.